All right. Good afternoon, everyone. Welcome to the Robotics Colloquium. It is my pleasure to have Marinelle Vasquez from Yale University today. I've known Marinelle for a very long time. We sort of grew up together in the HRI community. She's kind of the next generation for me. But she's been one of the most prolific researchers in the HRI community with lots of best paper nominations and awards. And she's won a bunch of other awards recognizing her research. Today's talk, I was very intrigued by the title. If you know me, I'm very anti-generalist anything, but I love that title and I'm really curious to hear it. So welcome.
Thank you. It's a pleasure to be here. So yeah, this is a brand new talk. So if you have questions, please, feel free to ask me. So I would say, very excited because it is the first time in my lifetime that I could imagine robots doing all sorts of things that when I was a grad student seemed absolutely impossible, right? And so it is, I would say, a revolution, if anything. And today I want to talk about this with Rosie as my example because, well, one, I grew up with Rosie, in case you haven't met this robot. And two, I think it, in many ways, sort of help us think about what the upcoming future may look like. And so for one, Rosie is very good at manipulating the physical world. And this is what you often get to hear, right, when you hear this term generalist robots. What people are really talking about are these generalist robot manipulation policies that are much more capable than what we had before. Now, I am a human-robot interaction researcher at heart, and so what is perhaps the most exciting to me is that this line of work is now starting to discuss people, right? And so we envision robots, for instance, working alongside humans in factories, providing elderly care or assisting in homes and offices. And Rosie, right, was a prototypical example of a robot assisting in the home. Now, the one caveat here, as an HRI researcher, is that whenever you hear humans, this is humans in relation to safety. Safety is, of course, important, but I don't think it encompasses the full picture that we often got to see in the Jetsons. Right? So for instance, Rosie sometimes had to take care of the kid and entertain him. Sometimes Rosie will bring the family together and take pictures of them. Sometimes it will help people relax and take a break from everything that was going on. And so the main message that I want you to get away from my talk, I'm just going to jump into it, is that these general purpose robots in human environments are going to need both physical and social intelligence. And by social, I mean the capacity to understand and navigate complex social relationships and environments. And so I'm going to try to kind of convey the way that I see things happening now in pictures. So we're basically building this super amazing robots that are in a very complicated real-world environment, like a real kitchen. And if there's a human, that human is sort of in the void, providing these natural language commands to the robot. But the reality, right, is that things are going to look more like this. You're going to have that human in the environment, and yes, they may communicate via verbal mode, but perhaps the human is sending other signals to the robot. Like maybe this person, when they say clean the fridge, and are holding a particular cleaner, they mean clean the fridge with this cleaner, but not in other ways, right? And so why this matters? Well, to me, this is important because now generalization is not just about being able to manipulate objects and physical tasks, but being able to have good robot performance in novel social contexts, okay? Now, this term, social context, this is fundamental for human-robot interaction. I'm going to show you here a paper from 2004 by Sarah Kistler and Pamela Hines, where even before the main HRI conference was founded, they were saying that, to design robots that behave appropriately will require a deep understanding of the context of use and of the ethical and social considerations surrounding that context. And so ever since then, we have been seeing a lot of papers in HRI that mention the context. In fact, I will bet that you cannot find a person in the field who says, no, social context does not matter. Now, for me as an academic, especially now that I'm trying to teach my students, the main question became, okay, we all agree on this, but what is it? What is the social context that we all talk about? And so for the last few years, with a couple of my students, we have been basically trying to come up with a concept that we believe can help unite different perspectives on this term. And so if you look at the literature, you're going to find papers that I can count with my hand, basically, that explicitly define context, with probably Laurel Rick's work being the most prominent. But then for the most part, the literature is extremely fragmented. People will use this term without saying what it means, and in implicit ways, they convey, for instance, the domain that the robot is in, like education, or maybe the task that the robot is doing, or maybe the social and physical setting, or maybe other things that, honestly, we had a hard time categorizing into one of these buckets. Now, the thing that we did notice when we were doing this review was that, first, there's a lot of factors in the social context that have to do with the environment. And this is what you get to see today for manipulation, right? Like the location of objects matter, the place that you're in matters, perhaps even lighting matters. But beyond that, at least in HRI, we also care about factors related to the agents. If it's a person, maybe you care about their personality, maybe you care about the way they look. If it's a robot, maybe you care about their level of autonomy. And beyond that, we also care about relationships between agents and with the environment. So, you know, what do I think that this person is thinking? Or maybe, what is my position in the world? And so with these ideas in mind, what we propose to do now is sort of think about this social context of a human-robot interaction as this set of attributes of the relevant agents, of their environments, and of their associations that influence the interaction. Okay? And so I'm going to use this definition as kind of like a motivating foundation for everything that I'm going to talk about today.
Yes, quick question.
In
the previous slide, I know that you're focusing specifically on human-robot interaction, but as you were talking about social context, which I think is incredibly valuable, I couldn't help but wonder whether such social context is relevant even in a non-human robot interaction setting. Like, for example, I have a ChatGPT window open and I'm talking to it. Like, clearly there is social context, even by your own definition of relevant to the agent, environment, and association.
So
is that like out of scope, or like do you
Yes.
think some of this could work there?
So this definition is actually heavily influenced by Anin's day work when he was a graduate student, when he was trying to think about what is context in ubiquitous computing. And so there he said, context is anything that matters for my application in the case of ubiquitous computing. And so when we came up with this definition, we were really thinking that first, these are robots that are embodied. Okay? And this makes a difference because now, in terms of the agent and the environment, you need to think about how that embodiment actually happens. Right? So for instance, if I have a person, imagine I have like a teleoperator, right? That teleoperator may be in a completely different environment than where the robot is. Now you need to think about two environments. And so when we're thinking about this definition, we really try to focus specifically in the case of there are agents that are embodied. Of course, we care about robots, so we're assuming there's at least one robot. And these sort of bounds and make differences, in my opinion, with sort of what you get to see in the digital world. Mm-hmm. All right, so now I want to talk first about why I think HRI is interesting, why it's hard, given this definition of social context. And then part two will be about how I see now large models changing the way we think about HRI, at least in the upcoming years. So let me start with point number one, which is perhaps the most obvious. And that is that, with my definition, the space of social context is huge, right? There's so many things that you can imagine matter for an interaction. And visually, I really like this plot that I got aware of, at least from the case of autonomous vehicles, right? When you think about autonomous vehicles being deployed in the real world, one of the challenges is that there's a long tail distribution of rare events that you don't get to see all the time, and that makes it hard to apply machine learning to these kind of systems. I think it's exactly the same for HRI. The big difference to me is that for autonomous vehicles, you at least have a manual of what you're supposed to do according to the rules of driving. But for a lot of HRI, we just have no idea of what is the right thing to do. And so a lot of things in this tail, we have never even imagined because we haven't experienced them. And there's no rule set that says, oh, this is the right behavior. Okay? And so a lot of the things that we have been doing in my lab for the last few years has basically been explore that long tail with a special focus on group human-robot interactions, because a lot of what you see in HRI is one robot and one person, and there are special things that tend to happen with groups. Okay? So I'm just going to give you one example along this sort of rare space. And this has to do with adversarial behavior. So if you look at the news, there have been a lot of cases of situations where people mistreat robots. There's many reasons why this happens. We can, if you want, talk more about that. But the reality is that robot abuse is a thing, and it happens in the real world. And so then the question for me as a roboticist is, what should the robot do? Right? Rule number 1 of robotics, you don't want to get back at people. What else can you do? And so our idea was, well, the robot is in a social context. There's perhaps other people nearby. Maybe the robot can convince other people to step in and help it. This is similar to what you get to see sometimes in sort of human anti-bullying programs, right? Now, I'm going to show you first an experiment that we did in relation to this, where C, who's now a professor at Northeastern, he pretended to be a participant. He was a Confederate, and there was another participant in there. And they were given this quote-unquote distraction task where they had to memorize Braille on a tablet. Okay, this was sort of the context of the experiment. And there happened to be a robot that the experimenter left there. And the robot would be sort of there kind of cheering for whatever was happening or being sad if they didn't do well. Okay? Now, Z, he was the Confederate. And so on purpose, he made mistakes. And when this happened, he put out his anger onto the robot. Okay? This happened initially with verbal abuse and then escalated all the way to physical abuse. I'm just going to show you the last example. And so the question is, what can the robot do to motivate that participant to tell Z, hey, you shouldn't do that? Okay? And so the control condition is the robot does nothing. Of course, we don't expect that to be very effective. And so we then tried having the robot have an emotional response. First, at the beginning of the experiment, it would look sad, and then it would kind of get angry back at the Confederate. Now, we had another idea. We also thought that maybe the robot should shut down. So I'm going to show you that now. So it looked a little bit sad and then shut down for 10 seconds and then went back up as if nothing had happened. Okay? And so this is what we found. First of all, in terms of physical abuse, it was obvious that it was mistreatment. We maxed out on the rating when we asked people, hey, did you see the Confederate, the other participant, doing this? But then, for verbal abuse, it turned out that the shutdown condition made people see the verbal abuse as more obvious abuse. And this was really interesting, right? It makes you think that, well, maybe robots should show some vulnerability, right? Now, the reality is that the experiment didn't work the way we had planned. Only 2 people out of 48 ended up intervening, saying something to the Confederate. And so for a while, I was like, no way this is going to work. Why would anyone get in conflict with another person for a robot that is not even their own robot in a situation like this? Right? Seems very hard. We don't like conflict. I don't like conflict. But then what happened was there started to be some evidence that conformity can emerge in human-robot interaction. If you don't know, conformity is a social group effect where if you are in a group with other people, if they all say, for instance, the wall is green, that sense of being in a group may motivate you to agree that the wall is green when the wall is white. Okay? And so there started to be some evidence that robots could do this in HRI. And so we thought, maybe what we did is social group influence. Maybe we add more robots, this would work. Now, one key detail for this type of effect is that people have to feel like they're part of a group. So we changed the task to be a collaborative task. So now we had two people, a Confederate and a participant, trying to do a physical task with 3 robots. The robots were just pointing at pieces that the humans had to use to then assemble a particular structure. Now, similar to before, the Confederate would mistreat one of the robots that often made mistakes here. And when that happened, in the control condition, nothing else happened. In the experimental condition, the other robots turned towards the mistreated robot and expressed sadness. Okay? And this was, to me, incredibly surprising. So we got more interventions in the experimental condition, but that's not the important thing. The important thing is that more participants intervene at least once, telling the confederate something like, you shouldn't do that. I'm going to show you one example of this. So here you're going to see the confederate on this side and then the participant over there.
Coming over. Don't break it.
Whoa, 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 don't break it, don't break it. That's amazing. Like, I can tell you this is very hard to actually see. Now, as you can imagine, right, we do all these types of experiments to understand what is possible in HRI. But the long tail is huge, right? What are the chances that we're going to be able to do experiments for everything that is going to happen there? And so more recently, we have been trying to come up with some theory that tries to explain, from a psychological perspective, how is this kind of robot social influence effect happening? Okay? This is, at this point, extremely simple theory. It's very conceptual, similar to, if you want, like the uncanny valley. But I think it's something that is very promising because we try to apply this model to different types of user studies, and it seems to be at least consistent with what we're getting there. And so I'm going to explain what this model says. So this is a model that is not for group interactions, it's for one-on-one interactions. How much social influence, in terms of magnitude of the social influence, would the robot have on a given person? Okay? So that's the dependent variable. The independent variables are, on the x-axis, whether the robot behaves in a way that exceeds the human expectations about the robot. If the robot exceeds the expectations, then it's more likely to induce social influence on the person. The y-axis is the other variable that is independent here, and that is how much the person feels like they're part of a group with the robot. So if people feel like they're part of a group with the robot, in the top, that means high social influence. If people feel like they're not part of a group with the robot, that means high social influence. If they're in the middle, probably not as much. Okay? And so I'm going to explain how you apply that to the last user study that I mentioned. I'm going to focus here on the interaction between one of the robots that expressed sadness and the participant that was in the study. Okay? Now, this plot, you see it from the perspective of the participant. The participant starts at the beginning of the interaction where the S symbol is. This is the start symbol. So at the beginning of the interaction, we told people the robots are going to be pointing at pieces in this interaction, so there's no reason to believe that you are exceeding expectations or failing expectations. And this was a group collaboration, so it's a little bit high on the y-axis. Now, in the control condition, the no response condition, the robots kept doing what we said they were going to do, so they stay in the middle of the x-axis. But then they were actually not very responsive. They weren't showing anything that kind of highlighted that group, being part of a group or collaborating in a very specific way that highlights belonging. And so we expect that to go down perhaps a little bit. Now, in the experimental condition, the robot expressed sadness. This was completely unexpected. So that would be more on the right side. And by expressing sadness towards another team member, probably highlighted that sense of belonging. So that would also be higher. And so now that model that I showed you before would predict that the sad response condition will lead to more robot social influence than the control condition that we have. Now, this is a very crude model, right? There's many things that we're not accounting for, like how things may change more dynamically over time, or how having multiple robots doing this may affect things. But I think it's a necessary step in HRI, because for the most part, we don't have theory that allows us to predict how things would happen in novel situations. And this is, to me, sort of a baby step in the right direction to try to get there. All right, now, question. Yeah.
Thank you. Do you think the way the bystanders, if I may use that phrase, like responded, affects how the humans feel about it? Like, let me take an extremal example, right? Like if all the other bystanding robots like cheered at the misery of this robot, or just turned around and stared silently at this robot. Like how do you think that, I was trying to place that in your graph,
perfect.
And I was trying to wonder.
Yes. So this is the challenge with social influence. So first of all, here for social influence, you're thinking about a change in behavior, right? What is the nominal behavior? The nominal behavior would be that people don't intervene, because that's kind of the context, right, of this study. The change of behavior would be people intervene, right? Now, this model doesn't tell you sort of the valence or the specific type of social influence effect that you get, it only predicts the magnitude of the effect. And this is a missing component for this kind of theory, right? And so when you say, right, like, is it that people, if the robots cheer, what would they do? Well, it may be that, you exceed expectations. I don't think you would be in high belonging, right? But at least you would definitely be more to the right. And it is possible that maybe the participant says, yeah, terrible robot. And they don't like the robot anymore, right? So that would still be a social influence effect, but it would not be sort of a quote unquote positive effect necessarily in the way that we were thinking about it in the experiment. Yeah.
There's a lot of overlap with his question, but the sad response is like one response. And just having a sad robot wouldn't necessarily make belonging increase, maybe? Or like, are there other emotions that maybe have more of a belonging effect?
I think that, for instance, if the robot could speak in language, you could imagine lots of different things that they could have said. Oh, poor teammate. This is definitely highlighting that group even more. To me, though, the sad effect, it does feel like there's something there in relation to we're all trying to collaborate together, right? And so that's why we thought it would go up. But I think, you could go even higher up, right? The challenge also with this model is that the way we created this paper is that I literally wrote code with some numbers that allows to make these plots so that the plots would be the same no matter the experiment that we were discussing from an implementation point of view, right? So like we weren't trying to hack specifically the color that we would get, because you can easily kind of get to that, but that's not the point, right? But the specific math that I used to create this model is arbitrary, right? We don't have data that allows us to come up with the actual numbers that fit, in a way, all of the XRI experiments that we have. And so at this point, this is why I was saying, right, this is more of a conceptual model, similar to the uncanny valley, if you wish, where, when you're in the dip, things are going to look weird. That's sort of the same level of complexity that we're thinking about here. But I think, it would be great, right, if we can get to a more explicit model.
I guess maybe, I don't keep reading this, but like, there's a whole bystander effect in like psychology of like when people yell help or in response. And I guess I'm just curious how that interacts with this.
Yeah, so again, this model is one-to-one right now, because it's just easier for us to come up with something that we believe applies generally. But I think in general for social influence, you would also have to factor that in. Like it may be that maybe you're in a collaboration with 10 other agents, and maybe there's a bunch of other people there that don't do anything. How that weights in versus this specific type of social influence effect, I don't really know. I would be making a guess. Perfect. Okay, so now, the second thing that I think is interesting about HRI is that the way that we often need to measure success is context dependent. And I'm going to give you examples of this. Now, to do that, I just want to jump in terms of group human-robot interactions to another part of this space, which is social robot navigation, which is arguably more to the left because navigation is a very common ability that you expect robots to have. And so Nathan, who recently finished his PhD at Yale, for many years, he was trying to come up with a set of tools that could allow our community to measure success, or at least better measure success in this domain. And one of the things that he did was create a simulation environment where we could easily, as a user, specify how pedestrian motion would emerge, including creating group interactions, so that in that simulation, you could see different types of social contexts emerge. Now, kudos to Nathan for, in a way, encouraging our community to use this simulation. If you want to try it, here's the link. The main thing you should know is that he's working on version 3 with a couple of other collaborators, and if you want to be a beta tester, you should contact him. Okay? Now, as part of this effort, we also worked on a big community paper on this topic, and I'll jump right to the good news. So as a community, we generally agree that all these things matter. One, safety is very important. But then there's also other things like how comfortable people are with people as it's navigating, legibility, social norms, politeness, and so on. The bad news is that Nathan finished his PhD, and if you ask me, what is the best navigation approach? My answer would be, I don't know. And it's not that the community is not trying, it's that it depends on the social context. Okay? Now I'm going to give you one example on this. So one of the things that we did was actually interview people, mostly in industry, and a few in academia, about how they would rank very well-established metrics for success. These are objective metrics. For instance, we had avoiding collisions. So the people that we interviewed generally agreed, if you asked to rank these metrics, that avoiding collisions is number 1, except for one person. Now, in terms of the other metrics, it was like, wow. I was not expecting this to be so extreme. It was really hard to find a pattern here. And it's not that, people weren't trying to measure success. They were, but everybody had different considerations. For this domain in the warehouse, this is what we care about. For the home, this is what we care about. So everybody, right, we're thinking about these metrics in a different way. Now, beyond objective metrics, there's a lot of sort of important subjective factors that we often care about, right? Like I mentioned before, do people feel comfortable with the robot? Do people perceive the robot as competent? Is it, navigating with clear intent, and so on. And so in HRI, the way that you would often capture these subjective perspectives is via surveys, right? You expose people to some interaction, then you ask them, hey, tell me, what do you think of the robot, 1 through 5, or something like that. Now, if you're a robot learning person, probably what you do is you get explicit human feedback. For instance, binary feedback, like thumbs up, thumbs down, or maybe demonstrations. And then you build a reward model that encapsulates, or you hope at least is consistent with those subjective perceptions. And so, as we were thinking about this problem in navigation, one thing that in a way became clear to us was that these explicit signals tend to be, in a way, much easier to gather if you have a human teacher that is dedicated to only teaching the robot. So this is a human that is there supervising the robot, and this is all they're doing. Right? This may be a person that maybe you hire to provide the data to the robot, or maybe a user that for whatever reason, all they're doing is watching the robot and telling it whether it's behaving okay or not. But the reality, right, is that at least for the home, we're going to see a lot of other types of interactions where that human that is there is probably going to be an active participant in the task. So for instance, right, imagine you have a kitchen, you have Rosie, you had a party, the kitchen is a mess, and in an hour you have family visiting, so you want the kitchen to be clean. So maybe you say, well, Rosie, I know you can clean it, but maybe it will take more than an hour, so I'm going to start cleaning with Rosie so that we get the kitchen ready, right? And so in these kind of situations, right, where you have collaboration or the human is an active participant, maybe you think, well, there's nothing we can do, but what we thought was, well, maybe we can still get feedback from people. We can get, in this case, implicit feedback. And so, you may see this, for instance, in the form of facial expressions. Maybe Rosie does something bad, and the person is like, what are you doing? Or maybe the way that a robot is navigating, if person is following, the robot does something, and people like, jump or do something different, right? There's all this other information that people just leak off that potentially robots can use. Now, I'm put here speech because oftentimes we communicate in ways that is not straightforward, what that means for a robot. And so the key difference here between explicit and implicit feedback is that the implications of explicit feedback for the robot behavior are clear. Because in a way, the human and the robot have made that agreement, right? If I say thumbs up, that means good behavior. But for implicit feedback, you often need of interpretation. Okay? And so I'm going to show you one of the early works that we did in this regard. This was during COVID. And in particular, Kate, she was very interested in this notion of how do we define good helping, okay? And so we had a very simple gaming environment that we asked people to play through an online study. This is, Space Invaders. You have enemies that are coming down that are shooting bullets. You, as a participant, you have a spaceship, and you can shoot up to kill the enemies. Now, the detail for this game was that there was also an autonomous agent, the orange spaceship. You got points for enemies on the left, and the spaceship got points for enemies on the right. Okay? And now, in the context of this experiment, what we were testing was how would people perceive two types of helping behaviors defined in relation to the score of the participant in the game. So in one case, this robot would come to this side and destroy enemies early in the game. In another case, it would only do so after it had destroyed its own enemies. Okay? Now, it was a surprise that this agent would go to the left side. People did not expect it. We didn't tell them that there was going to be any kind of helping behavior. So I'm going to show you just here one example. Okay. Now, our hypothesis was that if we were able to record people's faces, we would be able to guess how things are going. Are people liking the behavior or not? Okay. So I'm going to show you here one example reaction. This is someone that, said, yes, I'm willing to share my webcam while I'm playing this game. And at the time, the natural way you would reason about this is, okay, you get this face. You can use social signal processing to map that to emotions. It'll be a sad expression. Therefore, the conclusion would be the robot is doing something wrong. You need to change the robot's behavior. But even in this very simple scenario, what happened was that the human spaceship died because it was hit. It had nothing to do with what the autonomous agent was doing. And so the main key, easy point that I want you to take away from here is that if you're going to reason about implicit feedback, you must interpret it in context. Right? It cannot be that you just look at the person's face and then you make assumptions of that. You have to think about everything else that is happening in that social context. Now, after this, we decided to see, well, can we do this for navigation? And so we took advantage of that simulation environment that I mentioned before, and we had people, in this case, follow a robot to a destination that they didn't know in the virtual environment. And as they were doing that, we asked to record their faces with a VR device. Okay. So we had both their facial expressions, but also how they were moving in the simulation in terms of an avatar that they were controlling. I'm just going to show you, this is the rendering, right, of what the VR device is capturing. So what happened is, during the navigation task, as it was going, we paused at certain points in time, and then we asked people, hey, what do you think of the robot? Right, and so now we're surveying the person. Are the robot's intentions clear? Is the behavior surprising? And then they could answer, right, in relation to what they had just experienced. And so then the task was, can we take these observations of the interaction, the navigation patterns in the context of the environment, and the facial expressions, and then use machine learning in a standard supervised learning fashion to predict whatever ratings the person provided. So here you're going to see results for a multilayer perceptron, a transformer, a graph neural network, and a random forest. I'm going to show you specifically results for the 3 questions that we asked people. Is the robot competent? Is it surprising, its behavior? And are its intentions clear? And I'm going to show you binary F1 classification results. I can tell you, if you try to do this on a 5-coin scale, which is how we collected the data, this is really hard even for people. So people, we also had another survey where we asked people, hey, can you guess what that person was thinking of the robot when this happened? So that will give you a performance around 0.3. This is now just trying to predict positive versus negative perceptions. Now, in this case, what we found was that the random forest was generally similar or slightly better than how well humans could do this task. And maybe you're wondering, hold on, I like my neural networks. Yes, of course. But we generally have small amounts of data in HRI. This is data from 60 participants, which we collected over 3 months. And this is just not enough to train one of these models from scratch effectively, right? If you use a random forest, it's much better. Yeah.
And just to be clear, like 50% is guesswork? Like the line at 0.5 is guesswork?
I don't have it here, but no, because this data set is not balanced.
I see.
So a little bit worse than that. Okay. Now, we thought, well, we're doing like people. Can we do this in the real world? Now, one thing we learned was that if you remove the face, if you didn't have the face features, you dropped a little bit in performance, but not that much. And in the real world, where we have a robot with limited field of view, here we had a camera towards the front and the back, it was much easier to not have to worry about seeing the person's face all the time. And so here we try to do this, now considering the motion pattern of people in the context of the physical environment. And so here you have a robot. When it stops, it turns red. We survey them. And then when it turns green, it continues navigating towards the goal. These are, by the way, random people that were walking by that were willing to give us 5 minutes of their time. Sometimes, right, there's other people who are not necessarily following the robot, but we still capture them. And so the results that you see here in blue, this is, we use real-world data to make a prediction on real-world data. Okay? Now, results in green is we change the field of view of the robot in simulation to match what we could see in the real world. We train with simulated data from before that we had collected in the case of VR, and then we test in real world data. To me, the surprise to this, at least, was that we could actually use VR data to a big extent to get performance that wasn't sort of so low in comparison to the real world. Okay. Now, there's much more that you can do here, right? For the most part, this is reasoning about people's motion in relation to the robot, in relation to the goal in the physical environment. There's many other things that could matter that we're not considering. But I would say, I think it's very nice to start thinking about the potential of using machine learning to predict subjective performance for robots in real-world tasks. Right? And this is important because now you don't have to bother people all the time to fill out that survey, but you can imagine running a model more continuously. Right? OK. Now I'm going to go to part 2. So how do I see this large model changing how we're thinking about HRI? I'm going to use this graph, which, by the way, is still relevant. This is something that I presented when I was applying for faculty jobs in 2017. It's the same framework. We all use, in many ways, this framework in HRI to develop capabilities. So how does it work? We study human-robot interactions. We see how things go. That informs robot capabilities. Then we develop those capabilities. We evaluate them, and then we integrate it into the robot system as we keep sort of advancing autonomy. If you would like, to think about machine learning, you can think of this as the data flywheel, but with a focus on the user. Okay? So we're collecting data that helps improve robot capabilities, given what we think matters to people. Okay? Now let me talk first about the evaluation part here. So the first thing that I think is happening is that we can start having this scalability in terms of evaluation that I mentioned before, without having to really train models from scratch, which to me is quite outstanding. And so more recently, we have tried to do the same task, now with more real-world data. We're not using VR anymore. And we're testing, what if we pass this trajectory data and information about the goal as the robot is moving to an LLM and ask it, hey, why is the person that is following the robot thinking? And so these results show you how, in particular, Gemini 2.0 Flash does with in-context learning, just a few examples, which are either 4, 8, 16, 32, or 64, and how traditional supervised learning models trained from scratch, like a random forest, k-nearest neighbor, or GRU, do with the exact same number of examples. Okay? So, of course, you wouldn't expect a random forest to work with 4 examples only. Okay? Now, what you can see is that if you provide examples, you do much better than if you do zero-shot performance. But the other thing is that, even zero-shot performance in many ways starts coming close to what you do if you actually train a random forest with 64 examples, which to me is honestly outstanding, right? Because there's no data like this on the internet. This is a robot navigating at Yale in a very specific way, which is sort of, again, amazing that you can use these models for this. Now, what is perhaps even more surprising to me is that if you do the same thing, but now you provide 4 examples that come from the same test person. They're not exactly the same test example, because otherwise you have a data leakage problem. But if they're examples that come from the same person, you can actually do better than if you don't include those examples. And so to me, this is the very first results that I'm aware of that show the value of providing personalized demonstrations for ICL learning for doing this type of theory of mind tasks. All right, so the second thing I want to talk about is developing robot capabilities. And to me, the most exciting sort of space here is starting to have more open world reasoning in HRI tasks. And so I'm going to very briefly describe a paper that is going to come out at HRI in a few weeks. This is work that is led by Deb Asmita at Yale. By the way, she's in the job market. I don't know if you have positions, but just so you know. And so this paper presents BALI. This is bidirectional action language inference for goal prediction, which is an approach for inferring human goals in collaborative tasks from both language and action. And so let me go through the assumptions first so that we're clear on the setup. So here the assumption is that the space of goals that the human potentially has is open-ended. There's not a closed set. Now we're going to simplify physical sort of manipulation of physical tasks by having a physical state and action space that is fully observable. Okay, so we can assume that we have, for instance, action recognition for the person. And we're going to have shared physical action space, in particular because these are collaborative tasks. So the human and the robot can do actions that are within sort of the same space. These are all high-level actions. And then the human can express a set of preferences for the task in natural language, which can be potentially open-ended and ambiguous. So for instance, I want a savory dinner meal, something like that. And so I'm going to use Rosie as a walking example to explain this setup. So imagine you have a grandma that wants to cook because, you know, she wants to keep active, but she still wants the help of the robot, okay? And so what the robot wants to do is be able to help with the grandma while sort of minimizing the burden that it puts on her to having to explain absolutely everything that she needs. And so the grandma, she knows that she wants to make pasta, okay? However, the robot doesn't know this. The robot has to estimate the human's goal, and perhaps, you know, even this goal may be incomplete at this stage. And so because the grandma wants to make pasta, she starts by boiling water. Now, what she tells the robot is the following. She says, I want a quick Italian dinner, because the grandma is worried that she needs to finish cooking quickly so that she can have dinner with her grandson who loves Italian food. Okay? And so if you were to just use language here, right, if you just pass this instruction to a large language model, perhaps you conclude the person wants to make a caprese salad, because all you can see is, I want a quick Italian dinner. If you only use the actions, like boiling water, now you don't know if the person wants to cook a rice dish or a pasta dish. Right? And so here the setup is you can see both. And so considering that, the robot concludes that the grandma wants to make pasta, needs to be quote-unquote quick, and passes the pasta to the grandma. Now at this point, the robot is highly uncertain about whether the grandma wants a white sauce or a red sauce. And so it chooses to ask because it seems better to ask than just try to guess when there's very high uncertainty. And so here, what happens is that, well, the grandma actually hadn't thought that far, but now given that you asked me, perhaps she decides, I want red sauce, and so she says, I want a red sauce. And so the interaction continues. The robot passes the tomato sauce, and so on and so forth. Okay? And so you can think of this problem as a POMDP. There is the goal of what the grandma wants to cook. Let's assume it's not as complicated here. You know, it's predefined, although here in this method it could potentially change over time. And this is something that you want to reason about as the robot takes action, right? So that you can cover that. But here we don't assume any bounded space for the goal, so solving the POMDP optimally becomes intractable. And so what we're going to do is we're going to try to find an approximate solution, taking advantage of the world knowledge in LLMs. And so we're going to think about this problem as like online planning. The goal is to figure out what to do right now. And we're going to do that with receding horizon planning. So we're going to imagine how the interaction is going to evolve over a short horizon in the future, and then pick out sort of the most likely scenario there and take one action and repeat. Yeah?
Do we expect that like humans are talking to robots like very similarly as we would talk to another human like assistant? So,
Tell me more.
So in the example you were like, I want to make pasta, or like I want to make a quick Italian dinner. Is that changing like each one? You've kind of got a different, I guess, like vibe or like tone to it, right?
Oh, so the first thing I showed was what the person was thinking and then what the person actually said, which may not be exactly the same thing necessarily.
But like if I were to tell you like, hey, I want to make dinner tonight, it's like, I guess as a robot, I feel like I would say something slightly different, like
What would you say?
I'm going to make dinner, or like to like.
Oh, we're not worrying too much about those sort of expressions in the sense that, you know, the specifics of how would you communicate to a robot versus a human. At the end of the day, we pass this to an LLM, and we hope that, you know, can reason about language. But that's a good question. Actually, I haven't thought too much about how things would change in terms of now having a robot, and maybe people actually change the way, the specific words they use. Yeah, we're definitely not worrying about that. And so, okay, so we have a receding horizon planning setup. Now what's going to happen is we're going to use an LLM to come up with a set of candidate possible goals given the history of the interaction that we have seen. And this is possible, right? Because LLMs have a lot of world knowledge about cooking recipes. Now the other thing we're going to do is, given this set of possible goals, we're going to use an LLM to filter out the possible action space so that that tree doesn't grow up too fast and we can actually run this in practice with a robot in real life. And then we're also going to use an LLM as a judge to help score the paths along that receding horizon tree such that they're consistent with both the goals that we're estimating and also the language preferences that the human may have expressed in the past. Now, I mentioned before, right, the robot can also ask questions. And so whenever we're doing this estimation, we're also going to weight the sort of information gain that you may get from asking a question versus a cost of interruption. This is sort of a standard approach in HRI for coming up with questions, but it is actually very helpful here because there can be still situations where you're highly uncertain, and you can sort of simplify the task that way. And so I'm going to show you here results in terms of just using an LLM, using only actions, using GOOD, which considers language only but then applies Bayesian inference on top of that, and then BALI, where we don't ask questions and then ask questions. And so these results tell you when these methods, for the first time, start producing robot behavior that is consistent with the ground truth goal, and then the last incorrect guess in that respect. And so what I see happening in HRI, right, is that while there's a lot of interest in going completely fully end-to-end, there's a lot of potential for using these large language models to do this kind of reasoning that honestly, when I was a grad student, seemed absolutely impossible. All right, now let me get to the last point here. So in terms of studying interactions, I'm going to make an optimistic claim, in my opinion, for HRI. I think we're going to have less Wizard of Us. If you don't know this term, this basically means hidden robot teleoperation, rather than more Wizard of Us. And so let me explain. If you look at humanoids, right, you can now have them in your home. The caveat is someone may be teleoperating them. Now, in HRI, for a long time, probably more than 10 years, people have been arguing that we should move away from this kind of interaction. And the reason for that, or one major reason, is that if you have a human teleoperating a robot and then that robot interacting with people, what you end up studying is the interaction between the operator and the end user, which is mediated by the robot. Instead of, maybe you have a simpler robot, like this is Omi. This is a robot that was made at Yale that helps people practice breathing exercises. Or this is Shutter, a robot that we deploy on campus. If you have robots like this, where they're autonomous, well, then you're just studying the interaction between the robot and the user. Now, if you like to think about this from an ML point of view, I think the issue to me here is that you're going to get data of how users interact with a robot that behaves optimally, quote unquote, according to that operator. Whereas if you study this, now you get data of how users interact with a robot that behaves according to current capabilities. Right? And the challenge is, well, if you suddenly don't have the operator, well, you may have a distribution shift in the classical way you think about it, dagger, but in HRI with social consequences. So what do I mean by that? Well, it may be that now you're out of distribution, the robot does something crazy, and people are like, I don't trust this robot anymore, I don't want to use it, that's it. Right? And so what I think is going to happen in HRI at least is that we're going to keep pushing for autonomy, perhaps not tomorrow, general purpose, but still autonomy. And because of the capabilities I mentioned before, I think we're basically entering a systems era in HRI. And so what I mean by that, well, we're going to build more and more systems that allow us to do autonomous things better and better over time. This is number of paper submissions that happen at HRI 2025. I serve as the program co-chair. And the big surprise here is that the systems track had an increase of 34% of papers, surpassing the technical track event, which is, I did not expect this. Nobody expected this. And I think this is just one data sample of how important systems are becoming in the field. And so what I think is going to happen, right, is we're going to keep pushing for autonomy, still with a user-centered perspective. And because of these large models, we're going to get richer simulations, which allow us to be more confident of deploying robots in the real world. We're going to get more in the wild robot deployments, and we're going to get more robot learning from experience in the real world. And yes, this is going to lead to more data, which will lead to more end-to-end reasoning about social context and robot behavior. Now, this picture, while data is important, that's not everything that is conveying. I think there's still going to be very important questions for HRI from a machine learning perspective on how do we get here in a hopefully timely and effective way. And so just to give you one example, to me, one of the most interesting questions for machine learning in HRI is what kind of inductive biases we should be putting into these models so that we can generalize. And so if you haven't heard this term, inductive bias, these are the assumptions that the learning algorithm uses to predict outputs, given that it has an example that it has never seen before. This paper, by the way, is from 1980. If you like machine learning, you should read it. It actually discusses the importance of inductive biases for supervised learning, and it proposes things like simplicity or generality or maybe knowledge about the source of training data. And I think the question is, well, what should this bias be for HRI in a way that is general, right? It cannot be specific to a very particular problem. Now, given the definition of social context that I told you before, what we have been doing is sort of testing the hypothesis that we really need to model HRI data as relational data. And so what this entails is modeling that social context with graph-based abstractions. And if you do that, well, then you want to use machine learning methods or models that leverage that structure. Lately, we have been trying, for instance, graph neural networks, but perhaps in the future, it could be other models. This is just a sample of some papers that we have published over the last few years in this direction. I'm just going to talk about the last one over here. So this is a problem where we're trying to come up with a learn policy via imitation learning that we can apply no matter the number of people in that interaction. So if I train my policy with 2 people or 3 people, I can test it on interaction with 4 people and hopefully still works. And so the key to making this work is, 1, abstracting the social context as a graph, and then using graph neural networks to predict template-based actions for the robot. The nice things about the templates is that, if you get 1 more person, it's not like your action space suddenly increases by a lot. You just need to worry about 1 more person for which you have to predict who the robot is going to address, and then you pass that as a parameter for what the robot is going to do. So just to show you one example here with a data set that Sarah collected at KTH. Here we trained, like I said before, in interactions with 2 to 3 people, and then tested on a group with 4 people. And what you see here are sort of performance, more to the right is better, by a random forest, a multi-layer perceptron, which completely ignore the graph structure. You just stick your features into a long vector, and then the method that we propose, which is TGM. And so as you can see, if you think about this structure, it's much easier to generalize, even though we had limited data, like is often the case in HRI. All right, so I'm going to end here. The main idea that I want you to leave today with is that general purpose robots in human environments will need both physical and social intelligence. And what this means is that now when you think about success, you should think about good performance in novel social contexts. Thank you.
Questions for Magda? It's something you said about how, like back in grad school, if we had this kind of tools, we would be able to do XYZ. Like, are there other projects? I do feel like there's a lot of tendency to sort of take the latest thing and then not look as much far back into past research, and somewhat reinvent things with the new tools as opposed to kind of learning from the previous wisdom. Are there any projects off the top of your head that are kind of like, if you redid it today, you would have different results or different capabilities, etc.? Like, does that template apply to other projects?
So I will tell you one funny example. So when I was a grad student, I started working on group interactions, and we had this robot that at the time it told the participants in a study that it was going to be decommissioned by the lab. So the participants had to help this robot figure out what it could do in the lab so that it wouldn't be decommissioned. Okay? This was all an excuse so that we could test different orientation behaviors for the robot and different gaze behaviors for the robot in the context of the group. Now, at the time also, we didn't have super amazing sort of capabilities in regards to speech, right? And so I was the one deciding what the robot was going to say as the interaction was going, although the motion of the body and the gaze were autonomous, okay? And so I remember I created this whole UI for me to be able to go through the script of the interaction and click on things. We don't need any of this anymore, right? And one of the things that happened in that study was that accidentally there was one interaction where everybody knew each other. And it was a high cognitive load for me as an operator to decide what the robot is going to say next so that it looks reasonable and whatnot. And it happens that there was one person that spoke very lowly, very, very quietly. And we had a mic that was trying to pick up who was speaking so the robot could turn towards them in certain conditions, or the gaze could turn towards them. The mic would not pick them up. I was the operator. I was trying to hear via my microphones and headphones, and I could not hear the person speaking. So the person was completely ignored the whole way. And then when we asked participants, what do you think of the robot and whatnot, people were like, the robot hated her. Right? And I mean, maybe this still happens today, right? If a robot cannot hear someone, but I think a lot of this complexity in a way has dissipated, right, with latest technologies. Even speech to text is much, much better. And so, I feel like there's a lot that is changing that to me is actually very exciting, because the things that we imagine doing, now it's like I can envision actually trying to do them, right? And this is different than just saying, we're going to get to general purpose tomorrow. It's just that we can do so much more, I think, than what I could do as a grad student, or the amount of effort that you needed, that I think that also in many ways raises the bar for the type of interactions that now we can study, which is very exciting, right, in my opinion. Yeah?
Do you have any thoughts about, maybe for later how to include demographics? Because I remember back at home that we were using this paper robot, and they look kind of cute, you will think that maybe people wouldn't feel afraid of reaching out to the robot, but the response was completely opposite. Just people didn't want to interact with it just because the way that it looked, the way that it sounded, they were just afraid to that sort of interaction and hesitant to even reach out or to engage in the experiment. How to contemplate that in this sort of analysis?
Yeah, so I didn't talk about this at all, right? But the way that you introduce the technology is extremely important, right? And I kind of ignored that from my whole talk. But when you think about, just to give you a very tangible example, when you think about some of these scenarios, right? This example down here is one of my favorite ones, because you look at the video and it's like, wow. So this is Robovi, which is navigating in a mall in Japan. And then when it was just let there, it happened that kids like to bother it, knock on it, and push it and do all sorts of things. Now, I don't think this is sort of because kids are being, in a way malicious. I think they're curious, is my number one guess, right? But there are other robots here. Let me see. I think this robot, or at least a robot that was put in San Francisco, where the robot was like a police robot. And this robot was supposed to navigate by the sidewalk of this major company. And what the company wanted was to make sure that the sidewalk was clean and empty, but there's people who happened to live there. They were homeless. This was their home. And those people really wanted to sabotage the robot because the robot was invading their home, right? And so this is something that goes beyond just making robots, right? It's really more about how people relate to the technology and how it is introduced. And I think when you do user studies, this is something that, although we don't really talk much about perhaps, we need to think about because it matters a lot, right? And so I don't really have a sort of magical answer, a bulletproof solution to this, except you probably, from the very beginning, right, when you start thinking about what you're making, sort of think about people from the start. And then you guide this cycle by those needs and desires and requirements rather than just bringing technology and putting it there and hoping that, people are going to love that robot where maybe they don't even want it, right? Now, this is irrelevant of like demographics per se, but I think it's trying to get to the underlying issue that you were mentioning.
You mentioned a lot about sort of this long tail social context, right? Where maybe like in the autonomous vehicle setting where there's different pedestrian behaviors and different situations that arise. And something I've been thinking about a lot is like, okay, if we want to, study how human-robot interactions maybe differ by context, it also feels like we need to somehow characterize that context, like maybe break each of those contexts down into different axes so they're comparable. And so I'm curious about how you think about that comparison problem, because it's almost like, okay, it's just, a bunch of contexts, but we
If you want to work on this, I would love to work on this. Basically, Sydney, who's the student that was looking a little bit into this, she just finished up, so she didn't have time. But I can tell you a couple of things. In this paper, I think one of the coolest contributions is that you actually get a taxonomy of the different factors that we found in the literature that matter in relation to the environment, the agents, and the associations. It's not absolutely complete because we bounded our search to specific conferences, but it may be that there are more, but it's a very good overview of many things that matter. Now, the other thing that I think would be really interesting, and if anybody wants to work on this, I would love to collaborate with you, is to take as much HRI data that we can and try to build up some embedding where we can start reasoning about which social contexts are close to what. Now, here's the challenge. We have been trying lately to find a lot of HRI data sets that at least have data of what happened in the interaction, so like raw trajectory data, and then data of how people perceive a robot. And I can tell you it has been extremely hard to find data sets that we can use for this task. And so I imagine for the latter, it may be challenging to do in practice, but I think as a community, we need to start thinking about this because if there's anything that we have learned over time is that data can help, right? And so I think in HRI for a really long time, I think many people have steered away from sharing data because, of course, privacy considerations are important. But I think there are ways to think about how do you still keep things private, or at least you make sure you get permission for sharing data, and then you can actually contribute data that we as a community can use.
Thank you. All right, let's thank Marinel.